Welcome everyone to the IFIMAC-ICMM seminar series on condensed matter. We are starting today this new season of seminars, and I will be acting as a chair of this opening session. I'm Laura Arriaga from IFIMAC at Universidad Autónoma of Madrid, and it is my great pleasure to be here hosting today this seminar. So for those of you who are new to this series, let me remind you that you are unmuted during the talk, but after that there will be time for discussion and you will be able to unmute yourself and ask directly or discuss directly with our speaker. And now it is my great pleasure to introduce you Professor Luis Gonzalez MacDowell from Universidad Complutense de Madrid, who is going to tell us about fluctuating interfaces. His career, his research mainly focuses on interfaces because these are the places where two different parts of a system or two different systems come together and interesting phenomena happens. And he's going to tell us how to describe these phenomena using molecular simulations and statistical mechanics. So a little bit more about Luis. He did his PhD at Complutense University in the group of Carlos Vega. He defended in the 2000 and he did a postdoctoral stay at the condensed matter department of Johannes Gutenberg University in Mainz. And this was with Kurt Binder. After that, he came back to Complutense University as a Ramón y Cajal Fellow, which is the tenure track Spanish way. And in 2007, he got his tenure. And we are celebrating this week that a few days ago, he became full professor at the Physical Chemistry Department of Complutense University of Madrid. So now, without any more delay, Luis, the floor is all yours.
Okay, so good morning, everybody, and many thanks, Laura, for the introduction. It's my pleasure to have the opportunity to present the results of the research we've been performing over the last few years. I'm glad that you mentioned Kurt Binder, who sadly passed away about 1 week ago, where I learned from him all of the basics of interfaces during my postdoc. So this talk is the name of the talk is Fluctuating Interfaces, but I will be presenting results that I have been carrying out from over the last several years, but all have the common theme of the study of fluctuations. So the talk is going to be divided into 4 parts. First, I'm going to introduce the interfaces that I'll be studying and how we study the fluctuations within. Then we will apply this to the study of capillary waves of adsorbed films, which are the waves that occur due to thermal fluctuations on a liquid film. Then we will apparently make a big leap and go into the study of crystal growth. But what we will see, well, actually what I have found is that my previous experience on the study of capillary waves at fluid interfaces actually was really very useful to approach the study of crystal growth in ice in a rather different way than is being done conventionally currently. And then, since I'll be studying interfaces of ice, this will lead me rather naturally to the study of ice tribology. Why is ice slippery? Hopefully I have time to mention that also. So the interfaces I will be talking about initially are rather simple interfaces that consist of, that are made due to the adsorption of simple atoms such as argon on ideal surfaces. Eventually, at low temperature, you can get nice structures like this droplet here. But mainly, the system is simple because the intermolecular interactions are very simple, plain hard core plus attractive tail that we study in simulation using Lennard-Jones potentials. I will then move into somewhat more complex interface, which is the interface of ice with its own vapor. So essentially, the interface of ice in vacuum, which close enough to the melting point, actually is more complex than expected, because you get a layer of pre-melted ice. The first few layers of ice at the interface melt, and as you will see in the next few slides, this gives rather complex and unexpected behavior. So those are the interfaces that I will be talking about, but I will be trying to get rather general information from them. So the results are not really specific to those systems, particularly the first one. So the question is, why should we be concerned about fluctuations of these interfaces? And the answer is that measuring fluctuations is a very fine, non-invasive way of measuring properties of the interface. Okay, so if you think of traditional ways of measuring properties, what you do is to study how a system, your test system, responds to a perturbation. And so most measurements are actually invasive. And for example, if you want to measure the most relevant property of an interface, which is arguably the surface tension, for example, typically you take this ring here, metal ring, sink it into the solution, then pull it out and measure what force you'd require to create the interface. And that's an invasive technique. But there is a very powerful theorem, which is called the Fluctuation Dissipation Theorem, which says that actually the interface before being perturbed has all the information that you measure when you perturb it. So there are ways of getting that information without perturbing the interface at all. And the reason is that if you look, say here, in this region, very distant from the perturbation, you have an equilibrium interface. If you make a close-up, then you will see that the interface actually is not flat. The equilibrium state is flat because on average, the interface is flat. But if you look at it in greater detail, you will see that it has undulations. And so you have thermal fluctuations. And those thermal fluctuations will change the shape of your interface, and the likelihood of observing that fluctuation, which you can monitor by measuring the probability, actually is related via Boltzmann's ansatz to the free energy of the system. So by measuring the probabilities, you are getting information on the free energy cost of that fluctuation. And that free energy cost is conveying you information on the thermodynamic properties of the system without the need to perturb the system at all, just by studying the equilibrium properties. Mainly because when the system responds to some perturbation, it doesn't know whether the perturbation is external or it's just a thermal fluctuation. So that's the core of the fluctuation dissipation theory. So this is well known in experiment, and actually there are non-invasive techniques that you can do experimentally. For example, most small angle scattering experiments aim to probe the surface without strong perturbations and to measure its properties. Also, more modern techniques such as some frequency generation also study the equilibrium interface. So in theory, when you go to a book, a theoretically minded book, you can find very nice expressions which relate the intensity of scattered radiation with properties of the interface alone. That's the theory. But in practice, if you go to the lab, you always realize that there are secondary scattering processes, and you can have also scattering events in the bulk of the fluid, which are entangled with the primary process, which is the surface scattering. And so it is very difficult and sometimes to disentangle this mixing of bulk and surface information. So that's why scattering techniques do have this problem. And often you encounter that some very important problems have been discussed on how to analyze the signal. And these discussions have been going on sometimes for decades, as you can find if you look at this recent paper by colleagues in any institute for a given problem. Okay, so the way we study surface fluctuations is a technique that sometimes I like calling dream spectroscopy. Dream spectroscopy, which is a way of measuring the fluctuations in computer simulations. So in computer simulations, you can set up your system such that you get phase separation. And here I have a cartoon of some substrate that I'll be studying, which has an adsorbed liquid film. This is the adsorbed liquid film in my cartoon. And then there is an interface. This is the average positional interface. And on top of that, you have the bulk vapor phase. And the reason I say that this is dream spectroscopy is because you choose which are the atoms which scatter. It's something that we can do in simulation. So what we do is to look for the surface atoms. So for the atoms that are at the interface. That is actually easier said than done. But however it is done, the point is you do know what atoms are scattering. And once you choose those atoms, then you can create an imaginary surface which goes across all of them. And then right away, just by measuring in real space the deviation of your surface from the average position, you are getting real space information on the surface fluctuations. In practice, we'd like to make some contact with experiments, and in experiments, you rarely can measure real space fluctuations. Instead, what you measure is the Fourier modes of the fluctuations. So we need to take our real space fluctuations, make the Fourier transform, get the Fourier mode. And unfortunately, experiments never measure right away the Fourier mode. Instead, they measure the square of the Fourier mode, which some people call the correlation function or the structure factor, which is I will be calling this the capillary spectrum. Okay, so this is the spectrum of surface fluctuations in Fourier space. So we can do this right away in simulations with two advantages. One, we know what atoms are scattering. And two, we can choose the wave vector. There is no technical problem in doing perfect glancing angle spectroscopy. We just need to choose the components of the waves of the wave vector as we like. Okay, so once we've measured the spectrum of fluctuations, next thing we need to do is to find out what information does this spectrum convey. And particularly, we're interested in the thermodynamic information related to that spectrum. Okay, so to do that, we need to work out some little bit of thermodynamics. So consider we have a flat substrate and we have a droplet, and we'd like to know what is the free energy of this droplet. So in thermodynamics, what you do is to slice your system in very small slices. So for each slice, right away, you can find away what the height of the film is at that position. And so you go and you have a function which tells you which is the free energy of a film of given film height. Okay, that's a function that you know a priori. It's called the interface potential. That's the free energy as a function of film height. So for each film height, you get the free energy. And so that's more or less the free energy of this slice. But notice that actually the interface has a slope. So it's larger than the free energy you would have if it were flat. So you need to account for this increase of the surface area, which you do by merely simply measuring the gradient of the interface at that position. And that's squared, and then it's weighted by the liquid vapor surface tension. And this gives you the added extra cost of not being flat locally at this point. And then you sum this result over all of the slices, and you get the full free energy of the droplet. Okay, so that's my free energy model. And the notice that now this is a functional, it's a functional of the film profile. So this can be used to measure the free energy of an equilibrium droplet. But the interesting bit is that it can be used to measure the free energy of whatever perturbation away from equilibrium. So for whatever arbitrary film profile that you could conceive that is different from the equilibrium droplet, you can also measure the free energy. And so that's a way of measuring the free energy cost of the fluctuations. So now we need to relate this free energy with the spectrum of fluctuations. But it's a bit complex to do that for a spherical droplet. So the way we will test the model instead is by considering very simple geometry in which you simply put the film, liquid film, on top of a substrate. So that's an adsorbed liquid film on a substrate. And then still, on average, this film will be flat, but you will have, due to thermal fluctuations, you will have waves, undulations of the shape of this film, which increase the surface area and also the film height locally. And the interesting thing is that the free energy based on the previous model, and it can be worked out very simply for this geometry. And then for a given realization of a fluctuation, you can get exactly the free energy cost as a function of the Fourier modes. Okay, just in Fourier space. So you can transform the free energy as an expression of Fourier modes. And the interesting part, as you can see, is that the Fourier modes here appear as the squared Fourier mode. So clearly, we're going to be able to relate the free energy cost of a given fluctuation to the square of the Fourier modes. And so via this square, we can relate it to the spectrum of surface fluctuations. So in practice, when you do an experiment or you do a simulation, you're not going to get this for each possible configuration, but rather you'd like to do an average. So we need to relate the average of this to the properties of the system. I will mainly be concerned with the liquid vapor surface tension of my adsorbed films, okay? And the way you do this is simply by using the equipartition theorem, okay? It's a theorem we're very familiar with when we deal with monatomic gases. And there, the energy of the monatomic gas is just given by the square of the velocities. And if you plug this energy into a Boltzmann factor, this is going to give you right away a Gaussian distribution. And that leads right away to the well-known equipartition theorem for the mean squared fluctuations of the velocity. But if you look at the free energy of my surface fluctuations, this is completely analogous to this other form here. Only that the Fourier modes are playing the role of the velocities. Okay, so when I plug this energy into my Boltzmann factor, what I get is a Gaussian distribution of the Fourier modes. Okay, so I can get the mean squared fluctuations exactly as I got them for the ideal gas. And this is the main result that I will be using in the next few slides, is the result for the mean squared fluctuations averaged canonically over all realizations of this order. And as you can see, it's a function of Q squared, the wave vector, and the coefficient of Q squared is the surface tension. So how do we analyze our simulations then? Okay, we've seen that we can get the spectrum of fluctuations. So we average all of those fluctuations for a given film. And then what we do is to plot the inverse of those fluctuations as a function of Q squared. And according to the theory that I've shown you, the inverse of the fluctuations, that is the inverse of the spectrum of fluctuations, is just a polynomial in Q squared. So what we do is to fit our spectrum. We feed our spectrum to a polynomial, and right away, from the parameters of the fit, we get all of the relevant information conveyed by capillary waves. And most significantly, what we get is a measure of the surface tension, the surface tension of our system. So what we have done is to apply this idea to study the surface tension of adsorbed liquid films. We have a wall, which is a generic wall. We allow argon atoms to adsorb and make films of different thickness. Okay, so at low temperatures, I get this density profile. So this is the study of 1, 2, 3, 4, 5 different films of different thicknesses. As you can see, gradually this builds into the bulk density, but it's low temperature system, so you get very stratified density profiles. And now, for each of these films, I study the spectrum of surface fluctuations. And for each average spectrum of fluctuations, I'm going to get a surface tension. So what I'm doing now is to plot the surface tensions I get as a function of the film thickness. Here you have the results. These are my surface tensions plotted as a function of the film thickness. And if the film thickness is large enough, we get the expected result, namely that the surface tension is a constant. And we can check that these surface tensions are completely consistent to the surface tension measured by other means. But when the film thickness becomes smaller, we see that the surface tension now is non-monotonous and actually is picking up oscillations that we can check that are very much related to the oscillations found in these stratified films. Okay, and all of this region here with a surface tension that is actually not constant is not explained by plain capillary wave theory, by the classical model of capillary wave theory. And we've checked this is not just a coincidence and studied related system at higher temperatures for the different film thicknesses. There is less stratification, and then we still see surface tension as a function of film thickness, and now there are no oscillations. But clearly, when the film is thin enough, then you get an increase of the surface tension, and it can become about twice as large as the bulk value, or as the value of the thickest films. Okay, so this is not explained with classical theory, and so we'd like to understand what's going on. And so why doesn't the classical theory work? Well, if you want to make a theory for the fluctuation of the interface profile, you need to understand that studying the fluctuations of the interface profile essentially is a way of studying density fluctuations. Okay, so if the position of the interface is moving up and down, then you're having density fluctuations. So in order to get the theory for interfacial fluctuations, the bottom, the finer model that you need to address is a model of density fluctuations. And in traditional theories of capillary wave fluctuations, what you do is to ask, what is the density at a given point here for a given realization of the interfacial disorder? And in the classical theory, you say, okay, the density for this wavy film profile is going to be obtained from the mean field density of a flat interface. Okay, this is the mean field density of a flat interface. And only I need to take into account that it's being displaced by an amount L. And that's the classical result. And if you apply this result, you get that the surface tension must be a constant. Okay, but actually it's more natural to assume that the density at this point is not going to be given by the vertical distance away from the interface, which is just an arbitrary decision, but instead by the smallest distance away from the interface. Okay? And when you assume this, then extending this theory is just saying that the density now is going to be given by the mean field density profile of the flat interface, but as a function of the smallest distance away from that point. And it's a more complicated geometrical object, but is still amenable to theoretical analysis. And what you can see clearly here is that if now I perform some Taylor expansion of my density profile, I'm going to have terms which are linear in the square of the gradient. And the square gradient is a measure of the increase of the surface area. Okay, so all of the coefficients of this term are going to behave effectively as a surface tension. Okay, so if I work that out, which might look too abstract in that way, but I work it out, it's not difficult, but it's lengthy, then you get this very nice result. Okay, what we get is that the surface tension that you measure from the capillary wave spectrum is made of two terms. The first term, you could call it the intrinsic surface tension. It's the one that is given by the intermolecular forces of the fluid phase. But then there is an additional term, which is given by G prime prime. This is the interface potential. So it's given by the intensity of the substrate interactions on the liquid vapor surface. Okay, the substrate is not inert, it's making some force on the liquid molecules, and it's making some force at the interface. And this is measuring the intensity of those interactions. and it's multiplied by the square of the bulk correlation length. So there is this additional term, which if the interface is very thick, then it cannot fill the substrate, and then G prime prime is going to be 0, and you get a constant. Okay, but when the film thickness is small enough, then this term is finite, and it gives a contribution to the capillary wave surface tension. Okay, so given that, let's check the results. So are the results I showed you previously for surface tension as a function of film thickness in 2 different systems. And the good bit of this equation is that this function here can be evaluated by completely independent means from the study of capillary wave fluctuation. So we have an independent means of calculating this, and so we can check it very neatly. Okay, and so here are the surface tensions as a function of film thickness, and we test our theory with G prime prime obtained independently, and as you can see, it works very nicely, very nicely. Okay, it's not as nice here in this region, but these are really small films. So what this is saying is that if you're studying very thin films and you want to study them using some mesoscopic approach, where you assume that macroscopic surface thermodynamics can be extended up to very small distances with films that are just 2 molecular diameters, then the way to do that is by considering a film height dependent surface tension. Okay, you can no longer assume that it's a constant. Now, notice that the effect here is small. So you need to study, this is not accessible experimentally. To study the spectrum of fluctuations for such thin films, you cannot manage. But this has some implications in the study, for example, of capillary forces. So if you have 2 small colloids in a humid atmosphere, you find that often these colloids form a liquid bridge. So there's water condensing in between the colloids. And this condensation causes the 2 colloids to attract each other. And there is a classical expression based on plane surface thermodynamics for the force exerted between these colloids. It's given mainly by the surface tension and then just by geometrical properties of the liquid bridge. Okay, and some folks calculated these forces between colloids of several nanometers large. And then they attempted to describe those forces measured from simulation using this expression. And what they found is this result here. If you want that expression for the forces to hold correctly, then you need to assume a surface tension that depends on the film thickness, that is, on the thickness of the film covering the colloid. Okay. And so from the results of these folks, Laubeal, I could measure G prime prime independently also. It was measured here, and we apply the theory, and you get very, very nice agreement. So that would be a macroscopic manifestation of the significance of this film height dependent surface tension that in principle one could measure using, for example, AFM. Okay. Now, the conclusions obtained here are actually far more general than the implication of a film height dependent surface tension, because this expression is very general and holds for whatever external field is being applied on the system. So far, I have been considering that the external field is the external field due to van der Waals interactions of the substrate on the liquid vapor interface. But what about other external fields? So I think that it would be very interesting to extend these ideas to the case where you consider electric fields of atop films in electrolyte solutions, because electric fields can be very intense, and they can be also quite long-ranged. So this effect would likely be more obvious in this case. And so that was a proposal I suggested some years ago, and unfortunately it was rejected. So I have never been able to work on that any longer. But there is one simple case of external field that we are all subject to, which is gravity. Okay, so if I apply this equation to gravity, then I get this simple expression for the surface tension. The surface tension has the intrinsic value, but also, according to this theory, it picks up a value that depends on the gravity. You know, so this says that the surface tension of water on Earth is different from the surface tension of water on Jupiter. You know? The problem is, this is the bulk correlation length, which is in order of the Armstrong. So when you square 10 to the minus 10 meters, then you get a very, very small effect, which is completely not measurable. So this is just a result for amusement, but it's not one of practical significance, unless perhaps you approach very much the critical point. And then if the critical point, you're very close to the critical point, this is vanishing, and you might be able to measure this effect. But it's very difficult, I presume. Okay, but so the issue is that I could not pursue my project of studying role of electric fields on the surface tension. And so I changed project, and because I had no budget, actually. So I was inspired by this Japanese researcher, which is very interesting. So Ukichiro Nakaya was a nuclear physicist in the 1930s, and he got a position in Hokkaido, and he had no budget at all to do nuclear physics. But Hokkaido is a very cold city in Japan where you have plenty of snow. So he decided to do the most cheap research he could do, which was studying snowflakes. And so for some time he studied snowflakes that fell from snow, but then he decided to create snowflakes in the lab. And I was lucky to encounter a video of his work in YouTube, and it's so nice that I'd like to share it with you. So just for a break, let's see.
After 3 years, he had a breakthrough. This is Nakaya's own footage. On the tip of a fine rabbit's hair, he grew the first ever artificial snowflake. He discovered that by finely adjusting the humidity and temperature, he could create snow crystals with a huge array of shapes and type, just like those found in nature.
Okay, so he could create the snowflakes, and then by creating these snowflakes in the lab, he could measure how the shape of these snowflakes would depend on ambient conditions. And then the summary of his work is contained in this famous diagram in atmospheric physics, which is the Nakaya diagram, which shows the shapes of snow crystals as a function of humidity and temperature. Okay, so we're all familiar with dendrite-like snowflakes, which appear in postcards, but in Christmas cards. But actually, when humidity is small, the crystals grow in a much simpler shape. They always adopt hexagonal prism shape. But the interesting thing is that the shape of these hexagonal prisms will change with temperature. If you are close to the melting plate, to the melting temperature, sorry, the prisms will grow as plates. If you go down to -6 degrees, they grow like columns. If you further cool the system, they grow again like plates. And further cooling below -25 or so, you get again columns. And this is sort of an unsolved problem. And as you can see here from a divulgation paper in Physics Today, some time ago, well, the reason why this was happening was completely not understood. So I was motivated by this problem. And this leads us to the second part of my talk related to crystal growth. And it looks like a very different topic, but actually it's not. It's not, because we've been talking about how to study surface fluctuations in a liquid vapor interface. And we've seen that we can describe those fluctuations in terms of this free energy model, which is called the capillary model. But if we're studying crystal growth, now what we have is rather flat surfaces. And what we see is that the film heights, if you want, you could call this film heights, the film heights do not take arbitrary values. They take values that are congruent with the lattice spacing of the solid. So the smart way of studying this is then picking your capillary model, but just replacing your monotonous interface potential by a potential which is a sinusoidal function. And this is going to promote your film thickness or your film height, say, or the surface height, to obey exact lattice spacings. Okay, so it's just the same model with a different potential. Now, one reason I've been calling these free energies H for Hamiltonian is that if you look at this, the term here in parentheses, sorry, it's very much like a Hamiltonian. Okay, look at this. So here we have the derivative of a position, not with respect to time, but with respect to x, but the derivative of the film height with x squared and multiplied by the surface tension, which here is playing the role of an effective mass. So this is a kinetic energy. Okay, and this is a potential. So this is just a Hamiltonian. It's completely analogous to a Hamiltonian. So what we need to study is the problem of a particle moving under a periodic potential. Okay, but because this is a two-dimensional problem, fluctuations are very large. You cannot be happy just by studying the extremal of this Hamiltonian. You need to account for all fluctuations. So in order to account for all fluctuations, we need to calculate the partition function. Okay, so the partition function is going to be a sum of all realizations of film heights or of interface positions weighted by the free energy cost. And the free energy cost is an integral over my Hamiltonian. So if you look at this, then this has exactly the same shape as a path integral. So the problem of studying surface fluctuations is analogous to resolving a problem of path integrals under an external potential. Okay, so this allows us to make a very nice analogy of the role of fluctuations. Consider we were at very low temperature. If we are at very low temperature, then the surface tension is very large. This would be a mechanical system with a large mass. And if the mass is large, then you are in the classical limit. This means that your particle is going to adopt positions that are in the minimum of your potential. Okay, so at low temperature, I am only allowed to have film height positions, surface height positions that are congruent with the lattice spacing. Okay, but if I increase the temperature, then my surface tension decreases, which is like having a smaller mass. And then what I find is that my position is delocalized. So that's thermal motion. But eventually, the mass or the surface tension are sufficiently small that I start getting some probabilities of being in the forbidden region of my potential. And eventually, at sufficiently low surface tension, I suddenly get a complete overlap of the distributions. And that occurs at the roughening temperature. Okay, what is going on at the roughening temperature? Well, at the roughening temperature, none of the surface positions are privileged. So then the solid can take whichever surface position, and then it's behaving just like a liquid, like a fluid interface. By the way, this roughening transition was anticipated intuitively by Nicolás Cabrera many years ago, before it was actually discovered rigorously. Okay, so what we're saying essentially, there's an interesting analogy between the roughening of an interface and the metallization of a solid. Initially, we had the electrons at positions in the local minima, so like in the atoms, and eventually, if the electrons are too very light, or if the spacing between the atomic positions is very small, then you get a metal. Okay, so as far as the interfaces are concerned, what we mean is that there is a transition from the classical picture of a high energy solid with terraces and steps into an interface which is just like a fluid-like. This is still the bulk solid phase, but the interface will behave like a fluid-like. And so why should we care about this? It's very important because this is going to change completely the way crystals grow. Okay, as long as you are here in the faceted region of the interface, then growth is very slow. It occurs by two-dimensional nucleation, and it's an activated process. So it's very slow growth. However, if you go across the roughening transition, then it's like having many kinks in your interface. It's like a continuous interface. So whatever atom falls there is going to stick. And then you have very fast, not activated growth. It's linear in the saturation. Okay, so it means that the roughening transition has a great impact on how crystals grow. In practice, I'm interested in studying crystal growth on snow crystals. And snow crystals actually are more complicated because if you make a close-up to the surface, what you're going to find is that, as I mentioned before, that we have a pre-melting film. Ice and vapor phases are actually separated by a 1 nanometer thick sort of pre-melting film of water. So this interface is more complicated because it has to be described by two surfaces. One surface is bounding the pre-melting film from the bulk ice, and the other surface here is bounding the pre-melting film from the bulk vapor phase. Okay. So the way to study this is not with the simple sine-Gordon Hamiltonian that I showed before, but instead we need to write a model for the free energy that actually is the sum of these fluctuations, the energy cost of making these fluctuations, and the energy cost of making these other fluctuations. Okay, and the two film thick positions, film height positions, actually are coupled via this interface potential, which dictates the preferred thickness of this pre-melting film. Okay, and this looks very complicated, but surprisingly, it can be solved exactly under a Gaussian renormalization. And the result of that is the spectrum of surface fluctuations. But we have two surfaces, so we have results for the two surfaces. Fluctuations of the solid liquid surface, so fluctuations of the liquid vapor surface, and actually coupled fluctuations, solid liquid vapor. And you also find that this system has a roughening temperature. Okay, and it's very difficult to interpret these results right away, but it's very easy to do it graphically. So if you are above the roughening transition, where the interface behaves like a fluid, then you can write the spectrum of surface fluctuations, and you get that all of the fluctuations converge to a given point, which actually is the sum of the surface tensions, the sum of liquid vapor plus solid liquid surface tension. However, if you are below the roughening transition, then effectively the surface tension is infinite and all of your surface fluctuations diverge. So we studied this problem actually from computer simulations. We studied the fluctuations of the prism facet, that's the lateral sides of the hexagonal prisms, those are the prism facets. We studied their fluctuations, and very close to melting point, just two points away from 0 degrees, we found that they all converge, and that is consistent with the scenario of an interface which is rough. But if we decrease the temperature just by 6 Kelvin, then we see that the fluctuations now are divergent, and it's consistent actually with the picture of smooth interfaces below the roughening transition. So what this means is that the prism facet of ice, in a range between -2 and -8 Kelvin, it's undergoing a roughening transition. And what that means is that at this temperature, its growth rate is going to change completely. And we expected this would have some impact on the shape of the crystal habits. Okay, but as we have seen, the Nakaja diagram is actually quite more complicated. And so we also had to study fluctuations on the basal facet. On the basal facet, that is the base of the prism. And what we plot here in this column is the distribution of surface heights. So at very low temperature, we see that the distribution of surface heights behaves like a Gaussian. But if we increase the temperature a little bit, then we can see that suddenly it looks like a bimodal distribution, which means that on the basal facet of ice, you're going to like to have either one height or the other for the film heights. And you can see this in the contour plots. You can see clear patches of domains with different height. But surprisingly, if you keep increasing the temperature, then this bimodal distribution vanishes and you get a Gaussian distribution again. So what this means is that the basal phase of ice has three different phases. One smooth, low temperature phase, one sort of rough, intermediate temperature phase, and then a smooth temperature phase again. And this is going to change how the crystal grows and the speed of growth. And also we can map the fluctuations to our model. And when we do this mapping, then we get the parameters of the interface. And this allows us to measure the step free energies. What's the step free energy? It's the free energy that tells us what is the cost of growing the ice crystal. And so we have results here for the basal and the prism phase. And so we see that at close to 0 degrees, the step free energy of the basal phase is higher than that of the prism. So what that means is that the prism phase is going to grow faster. And if it grows faster, it's going to make plates. But then if we decrease the temperature further, then suddenly is the prism phase that has step free energies that are larger, which means that the basal facet is going to grow faster. And then you get columns. And then further decreasing the temperature, the basal phase gets step free energies that are larger, and then the prism phase grows faster and you get plates. So by our computer simulations, we can explain at least 3 of these regimes in the Nakaya diagram. They look just as the expectation from the Nakaya diagram. And that's why Nakaya wrote this beautiful haiku, which says, "Snow crystals all at ascent from the sky." Because just by exploring the shape of the snow crystals, you can tell at what temperature and what humidity they grew 10,000 feet above Earth. Okay, and now I'm not sure how much time I have left.
You can have 5 more minutes if you want.
5 minutes. Okay, so then I'm going to skip this bit, and I'm going to go to the study of why is ice so slippery. Okay, which is a very, very interesting topic related to the history of science. So it has been discussed for a very long time. So the first hypothesis of why ice is slippery was due to Faraday, and he suggested that ice actually has a pre-melting. We've seen that in simulations, and he said this would act as a lubricating film. So when you put your skater on top of ice, then it's lubricated, and so you have low friction. But James Thomson, who was the brother of Lord Kelvin, he argued that this could not be, and that instead, what happens is that because you have asperities here, then when you put the slider on top of ice, the pressure is so high that it melts. And he suggested this because he was the one who discovered that ice melts under pressure. Okay, so that was his hypothesis. And then eventually Bowden, he argued that this could not be the case, that the pressures attained here in these asperities could not be equal to the melting pressure. And so what he suggested is that when you have sliding, then the sliding is heating ice, and by heating it, you are melting it. Okay, so we decided to study this problem because we had already experience in making these pre-melting films. And the only thing we do is to put a substrate on top of the pre-melting film and then allow it to shear. Okay, so let's see what happens at -8 degrees. Okay, what we see is that clearly a pre-melting film forms. And when you shear it, you get a clear pattern of laminar flow. This is Couette flow, exactly as expected in lubrication theory. So definitely we can show that at temperatures not too far away from 0 degrees, ice has an interfacial pre-melting film, and this behaves like a lubrication layer. So in that sense, Faraday was right. Now, if we go to lower temperatures, look here. Now the pre-melting film is really very thin. That cannot do any lubrication at all. But then let's take a look at what happens. It's going too fast, I think, but let's see if it repeats again. Okay, did you see that? So it was just 2 layers thin, very thin, but in just a few nanoseconds, it's becoming thick enough. And so if you look here, in 5 nanoseconds, you are at much lower temperature, but the film thickness is just as large. Okay, so to summarize, well, no, not to summarize. All of these simulations were performed just at 1 bar pressure, which is very low. And so experts in tribology, and there was a recent paper by Daniel Bond in Nature, would argue that because of the asperities, the pressure on the asperities is much larger than 1 atmosphere. And it's a well-known phenomenon in tribology that when the pressure is very large, then the lubricating film is being squeezed out. And that's why water is a bad lubricant usually. It's nice that it has a low viscosity, but it can be very easily squeezed out. And when it's squeezed out, then you are left with the bare contact and you get large friction. So he argued the pre-melting film cannot be the reason for the low friction phase. But you know, you need to take off your tribologist suit off and put your water expert suit on and take a look at the phase diagram of water. So consider that we are initially at 1 atmospheric pressure. And because of the asperities, the film here at this pressure increases its pressure. It's being pressurized, okay? It's compressed. So you increase the pressure, what is happening? You are approaching the melting line. So this means that the free energy cost of making a pre-melting film, which is liquid water essentially, is actually smaller. Okay, so we studied the film thickness of our pre-melting films as a function of pressure for all sorts of different substrates. And for whatever substrate, what we found is that the film thickness is increasing with pressure. Okay, so there can be no squeeze out. You're moving away the equilibrium position to actually thicker films. Okay, and I think this summarizes some of the key features of ice slipperiness. First, we found that you have spontaneous interfacial pre-melting as suggested by Faraday. So that provides for self-lubrication. Now, if you compress the film, then you get actually increase of the film thickness. So it's related to the hypothesis of James Thomson of pressure melting, but it's not quite pressure melting because the pressure is well below the bulk melting pressure. It's a surface phenomenon, okay? But it means that these lubrication films are self-healing, okay? And when you get sufficiently high sliding speed, then you also have frictional surface melting. And this gives a mechanism of feedback growth of the film that is also occurring well below the melting temperature. Okay, so these are perhaps some of the keys of ice slipperings, and we got this accepted just 1 week ago. Okay, so I'd like to finish thanking all my collaborators. The early work was done in collaboration with Jorge Benet as a student. Then all of the work on ice, most of it has been done by Pablo Llombar. Some of very interesting results I couldn't discuss here were done by Juan Luengo, who is now at your institute, and by Lucas Baran. And I'd also like to thank collaborators like Pedro Tarazona and Enrique Chacon, who taught me how to study capillary wave fluctuations many years ago now, and my recent collaborators, Noja and Andres Guerrero. And thank you for your attention.
Thank you very much, Luis, for such a beautiful talk. I think we learned a lot about fluctuating interfaces now. And we have time for questions. Please let me know. You can use the raise hand button or directly unmute yourself. Okay, I can break the ice. Oh, there is a question by Olivier. Please go ahead.
Hello, Olivier.
You are muted. Please unmute yourself.
Hello,
Yes.
can you hear me?
Yes, yes. Hello again.
So thank you very much for this very nice seminar. I had a question about the first part, because I was actually a bit confused when you mentioned this correction to the surface tension in your formula with the G second, because when interface gets close to a substrate, so in my view, there's two effects. One, which is that it sees the potential induced by the substrate, but also because of the layering of the fluid that you mentioned, the liquid becomes anisotropic. And so as in the case of solids, in this case, the prefactor of the Q-square term is not the surface tension, it is the stiffness, which is the surface tension plus the second derivative of the surface tension with respect to the orientation of the surface. So I did not see a distinction between surface tension and surface stiffness in your studies of liquid films influenced by the substrate. So could you comment on that?
It's a good point, and actually you're right. Yes, eventually, if you have a very stratified film, then where is it? Here, when the film is thin enough, likely you have anisotropy. But no, you don't have anisotropy. Well, let me think. It depends on the structure of the layering. Yes, but it's true. One should study both fluctuations in two different orthogonal directions. And it would be interesting to study whether there are differences. But anisotropy in cubic crystals or in closed-packed crystals is usually
anisotropy even in layered films. I think the free energy of a surface should depend on its orientation if the fluid is layered. So then the prefactor of the Q-square term in the spectrum should be a stiffness.
Yes, I understand that you should get a coefficient times qx squared plus another coefficient times qy squared. And one could test whether there is a difference in the stiffness coefficient depending on the orientation of the fluctuations, in the orientation of how the fluctuations are propagated. And we have done that when we have studied ice, and we do see anisotropy in ice. But we haven't studied for the adsorbed films, and it's an interesting point that one should do. I presume that we averaged over all directions, and so our surface tension, which is actually an average of stiffness coefficients. But notice that these are argon atoms, so the likely structure close to metallic, close to solid crystalline structure, it should be close packed. And in close-packed geometries, the anisotropy is rather small.
Okay, thank you.
Okay.
Thank you, Olivia. Any other question? Okay, Luis, I'm curious, probably you said, and it's just that I missed, but also on the capillary waves, you have, when you first introduced the equipartition theorem, you have a term that is tau of the capillary wave that goes with q to the fourth?
Yes.
Which one is that?
Okay. Where was it? It is. Yes. That's right. You also have this term. So in the introduction, I have been discussing only this term. In the general theory, actually, you assume that this surface tension depends on the wave vector also. And so that generates essentially a new term, which is called the bending rigidity. Okay, so it's a very tricky coefficient because it is well defined as far as you can define a surface. And you know, when you go to Q small enough, I mean large enough, then the way you decide how the surface is defined is arbitrary. You cannot avoid it. The terms that are meaningfully defined are in the limit of 0Q vector. And so this one is sort of ambiguous, but some folks in your institute will argue that subject to some arbitrariness, you can at least argue about its sign. And for liquid vapor interfaces, you can argue that it should be positive. I say this because depending on the way people have traditionally defined the interface, sometimes it looked negative. I know that's positive. But that is because of the first slide of my talk, or first view, where I discussed that there is an entanglement between the bulk signal of the spectrum and the surface signal of the spectrum. And depending in the way you disentangle this, you can get negative or positive bending rigidities, which has been a concern for some people for many years.
Okay, thank you a lot. If there are no more questions, I want to thank Luis again for this great talk. And please join us again in 2 weeks for the next seminar. Thank you.
Many thanks.